Hey, Bryce Carlins here at FRC Worlds 2017 in Houston. I'm here with Elena from Team 118, the Robonauts. I'd like to talk a little bit about kind of their unique robot design, their kind of advanced design and fabrication work. Specifically, and I think a lot of teams are most impressed with this year is your turret and the implementation of that. Can you talk to me a little about like the design, like how you came to the conclusion that you need one, and then what went into like the design as far as like the specifics of how you fabricated it?
Yeah, so we actually started our design process with the idea that we were going to have multiple streams. And after a lot of prototyping and a lot of unsuccessful designs, we decided that we would only want one stream. And we figured that if we were only going to go with one stream, we figured it would be beneficial for our autonomous mode to have a turret so that we can go to the hopper and immediately start shooting.
Very cool. A couple things I noticed. I noticed you have like unique wheels. I haven't seen flywheels very much like that on any other teams. And also your counterweights are just like massive. I haven't seen a lot of teams even like use counterweights. So what kind of went into that?
Okay, so our turret has two Fairlane wheels, and to keep our inertia up, we have a separate 1-pound brass wheel, which is to the side over there. And we actually power it with another 775, which is and it has a pulley ratio of 2.5 to 1, which is attached to the normal Fairlane wheel, and it allows us to have 6.25 times more inertia. And so instead of having a super heavy flywheel to begin with, we can separate it from the flywheel in order to have a more efficient and lightweight design.
So you actually have the flywheel gear on a different ratio, geared up higher speed than your flywheel.
Yes. Our inertia wheel is running at a faster rate than our flywheel.
That's very cool. That's something I haven't seen anywhere yet, I don't think. That's a very neat solution. So you don't have to have as much weight. It's more effective.
Yeah.
Another problem that I've seen you guys tackle in a very neat way is the feeding system. That's what I think a lot of teams had like very good shooters, but their feeders were just subpar and it was like didn't do service to the shooters. So what went into like the feeder design with all your like separate belts?
So we actually had a lot of different feeder prototypes going. We had one that was kind of similar to 148's design with the spinny thing, and we had another that was with like Mechanom wheels, and we just tried a bunch of different designs, and we finally ended up with the pulley system because it was the most lightweight and it was the most effective at traveling the balls from the intake and the ground to the C-roller, which is at the back, which helps push it into another belt that lets the balls go up into the turret.
So I noticed when I was watching your reveal video initially, the belts that run, like there's like all the belts that run through the hopper, and then like the one line that goes like straight into the shooter at the end that went a lot faster. So you talked to me about like, it seems that you were like really accelerating them a lot before they even touched the flywheel. Was that like a definite part of your design?
Yeah, so we have a couple things going into that. We have like springs that force the belt right underneath the turret into the flywheel. We also have a trigger wheel, which is ran on a separate bag motor than the flywheel itself, and it helps push the balls from the belt system back into the turret.
Awesome. All right, we're here with Carson, and he's the electrical pneumatics lead, and we want to specifically talk to you about your pneumatics implementation and how you design for pneumatics, and like how you design your mechanisms for linear actuators, and then also a little bit like specific about how you did it this year.
So we tend to favor pneumatics over motors for simple actuations because they're Boolean, they provide force that doesn't stall out, and they're very, very fast. This year we have pneumatics on our gear grabber because we wanted a quick just up, down, and close, and we felt that we could get that better from pneumatics than we could from motors. One of the cool things on our robot this year is a linear gear ratio because we needed to fit a 10-inch stroke in a 5-inch space. A 10-inch stroke on a pneumatic turns into 21 inches if you add on the extra stuff. So we used a rack and pinion to double the amount of travel you could get from a pneumatic.
Wow. That's a very cool system. Um, so when you're doing your like kind of design CAD work, um, what goes into like getting like the joints and everything, and like trying to figure out like how you're gonna mount everything? Because I think from my perspective, a lot of teams struggle with pneumatics from like a mounting perspective.
So before this even goes into CAD, this starts as prototypes.
Right.
We have boards off that can provide pneumatic power without a full robot, which helps us narrow it down. We tend to use just a pin in there so it can rotate freely. Rod ends also help because they have not only the pin joint, but also a little bit of theta movement that allow you a little bit of wiggle room.
Okay. Awesome. Thank you very much.
You're welcome.